the process of coming up with a proof, really the scratch work, and the proof itself, the write-up, end up looking very different from each other. So I wanted to kind of go through an example which is found inside Joe Gallien's textbook, Contemporary Abstract Algebra. We're going to look at Euclid's Lemma, and if you're looking at a different textbook, I think that's fine. The thing is, we will use a theorem which is presented in the book just right before Euclid's Lemma. So I hope you can follow along if you're using a different textbook. I am using the 8th edition of Joe Gallien's book to go through what's going on here. What I ended up doing was writing a proof on my own, and I didn't use the same variables that Joe Gallien did. So what I did was I fixed anytime I used a variable that serves the same purpose that Gallien did, I ended up using his notation. So you can kind of follow along this slightly more thorough proof along with what he has as well. But I hope to demonstrate a lot of the key ideas of how you go from the scratch work to the proof. So here's what I do is I just sort of write the statement that I want to prove first, and let's state the things that we have, especially the setup sentence where there's nothing other than, okay, we've got let P be a prime, let A and B both be integers, and then if you're trying to prove an if something then something statement, you should suppose this first part to be true. So we're going to suppose or hypothesize that P divides AB. There are two things that can occur. This particular proof works nicely by cases to either note that P should divide A or P must not divide A. It's one of those two things that has to occur, either to be or not to be, right? So P divides A or P doesn't divide A. If P divides A, look, we're done because OR is so soft, right? So you only need the conclusion of P divides A or P divides B. So if P does divide A, then of course this OR statement's already true. So we're actually going to add in the extra supposition that P doesn't divide A. So we're going through this second case because in this first case was so easy, we're already done. Second case, now if P doesn't divide A and we're trying to prove P divides A or P divides B, it's going to be impossible to prove P divides A because P doesn't divide A. So we're going to have to now try to prove that P divides B, and so we'll state that out right here, right? So in fact, what we finally want to show in the end, we're going to state at the bottom as a therefore P divides B. We don't know this yet, but this is what we're trying to get to. The line above should basically unravel the definition of what P divides B means. Okay, and otherwise we're done with the cases stuff, so I got rid of that. Since P is prime, and since P doesn't divide A, the GCD of A comma P, the GCD between these two integers, has to be 1. That's just think about what happens with a prime. Okay, so then I'm going to cite for you theorem 0.2 in the text. This is the same notation Gallien uses, but if we replace the B here, so non-zero integers A and B, if we replace the B here with P, then we have AS plus PT is equal to GCD AP, but we know GCD AP is equal to 1. So we're going to apply this theorem using the A in the theorem is the A that's stated here, and then the B in theorem 0.2, we're going to plug in P instead essentially. So we will get there exists S and T by the theorem, which are integers such that AS plus PT is equal to 1. So now we're done with the theorem. We can multiply both sides by B, and I distributed on the left. Now we haven't actually used the fact that P divides AB yet. We just sort of stated that it does, but since P divides AB, we get from this P divides AB, so there is an integer x such that Px is equal to AB. It's just what the definition of division is, right? Just divides, that is. You can take this equation and multiply both sides by s, and so you get Pxs equals ABs. Now why did I do that? I did this simply because I stared at this equation, which we know to be true, and there's this ABS. So by multiplying both sides by s, I stared at this AB and this ABS, and I said, I don't know. I don't know what to do. So I just multiplied both sides by s, so I have ABS. So this first term can be replaced with PXS, and that's what I did here. So this equation rewritten here, just replacing the first term. You can factor out a P just using standard algebra, standard high school algebra right there. And it's at this point, it would have been really nice if we had just somewhere earlier said and defined this new quantity y. If we just said y was xs plus tb, what's in parentheses, then we could say p times the stuff in parentheses, or y, is equal to b. That'd be so nice if we had just defined this y. And the place we can define y is actually right here, right after this period. See, we need x, and x is defined right here. We need s and we need t. Those were defined in the previous previous sentence to that right there. And we also need a b, and that was way up here. That has existed for quite a long time. So this is really the first spot right where this blue text is, where we could have said y should equal this. Okay, and it may seem strange to the you might worry that it would be strange to the reader to read that right there, and it sort of is. It sort of comes out of nowhere, but it will make the flow of the later part of the proof much better to include a statement like this earlier. You'll see that in a second. Also, when you do your scratch work, it turns out that you'll get sometimes things that are true, but maybe not exactly necessary. There's a way to work it around. So instead of, I mean, yeah, I multiplied by s on both sides, but instead of doing that, what if I just, well, look at this ABS. What if I just replace the AB part of the ABS with PX? Then I just have PXS right away. So I actually didn't need to write this equation down. But, you know, I'm being honest, it's the way I discovered things. And so there's sort of a way to say, well, here's the idea, and we can clean that up. Now, and then we're so close to done here. So B equals ABS plus PTB, that's from right there. And then we did this replacement using this equation, and then we factored. And then finally, if we had just said y was equal to this, we could do this really easily. And now P times y is equal to B, therefore P divides B. From here, sometimes you'll want to just go ahead and write the proof, and that's fine. But if you have something that's a bit more complicated than this, you might draw a dependence diagram. So I'm going to try that here, even though this one's not too complicated, just to make sure we have all the pieces in some sense of order. So P's prime, A and B are integers. Suppose that P divides A times B. So given the A and the P, either P divides A or P doesn't divide A. If P divides A, we're done. If P doesn't divide A, the GCD of these two integers is 1. By theorem 0.2, there exist integers S and T such that this equation is true. Multiply both sides by B, and I distribute it on the left. We also have from P divides AB. See, it's sort of clear that we haven't really done anything with this yet. So that's why I like these diagrams. Just the definition of P divides is now there exists an integer x such that Px equals AB. It's at this point in the proof that we could, you know, define y. We could say that y is equal to xs plus tb because x has been defined here, and s and t have been defined here, and then b had been defined way long ago. Finally, we can place all these. This is just copied from the last slide, but we have that b equals all this from right here, and then this equality is just from right here, just doing the replacement that ab is the same as px. And then the next step has no need, there's no justification using earlier stuff. This is just standard algebra stuff. And then finally, this last part, the justification is this equation right here, that y is equal to xs plus tb. And so again, because you have p times y is in integer, so p times y is equal to b, therefore p divides b. Now I think you can see sort of clearly the flow, and it helps to see what has been used by doing a diagram like this. And here's how you'd finally write a proof. Whether you're going to type a proof or hand write a proof, this is what a final proof looks like. Here's the statement of the theorem, and then we'll state this sentence basically as is. Suppose that P divides AB, either P divides A or P doesn't divide A. If P divides A, we are done, so suppose that P doesn't divide A. Since P is prime, the GCD of A and P is equal to 1. By theorem 0.2, there are integers S and T such that AS plus PT is equal to 1. We can multiply both sides by B, and I didn't even explain it that way. I just said thus. You know, the reader can really figure out that you've multiplied by B on both sides. Since P divides AB, that's from up here, we haven't used this yet, at least in this paragraph proof. Since P divides AB, there exists x in Z such that Px equals AB. Define, or you can use the word let. Okay, let y equals xs plus tb. There's actually, oh, and then in Z, two things going on. We're defining y, and also we're just stating that this thing is in Z. Now, should we prove that this is in Z? Well, yeah, maybe, but that's not really the key part of the argument. I think at this point, to argue that the product and sum of integers really is an integer, sort of breaking the flow of the argument. Of course, this is an integer. The key point was to define the right quantity y. What was the right thing to multiply against p? And we now know it's y from our scratch work. That's really the point. I used then here because I didn't want to start the new sentence with notation like b. So then b equals, and then all these equalities, you don't need to do anything to explain them. The reader can go back and should be able to look at each of these equal signs and goes, oh yeah, I know why those are all true. And again, this last one was right here, right? And notice there's a period right here at the end because that's the end of a sentence. Then this, which equals this, which equals this, which equals this, finally equals that. And then since py is equal to b, we actually have p divides b. And you could sort of end it here, but I feel like right now it's good to just state outright the thing that appears after the then. Therefore, we have P divides A from up here, or P divides B from right there, and then a box to end the proof.